Welcome to qnawire.
In this problem, we need to solve for the angular velocity of the bar and the velocity of its mass center upon impact. So I have here a sketch of the problem. So the bar with mass m, so 5 kilograms, initially rotating at angular velocity omega 1 with a value of 6 radians per second, hits a latch producing an impulse at point A. So as you can see in the second part of the diagram. And causing it to rotate with a different angular velocity omega 2 and move its center of mass to move with a linear velocity v2. So as you can see in the last part of the sketch. And as you know, we can express the linear velocity in terms of r and omega. So for the velocity before the impact, so the velocity, the linear velocity of point A, so A1 is given by, so L over 2 omega sub 1. So this is directed downward. So since the bar rotates about the center point G, which is at a distance of L over 2 away, and it's downward because as you can see in the sketch, we assume that it's initially rotating in the counterclockwise direction. Now, after the impact, the velocity at point A, so VA2, is equal to negative E VA1. So, where E here is the coefficient of restitution. So, substituting the equation for VA1, so this would be equal to, so L over 2 E omega sub 1. So this is pointed upward, so we omit the negative sign there. So since as you can see in the diagram, the bar rotates in the opposite direction after impact. So hence, the linear velocity V2 after the impact is equal to, so VA2 plus L over 2 omega 2. So substituting the equation for VA2, so we'll have, so 1/2 LE omega 1 plus 1/2 L omega 2. So applying the impulse momentum theorem and solving for the moments about point D, taking the counterclockwise direction as positive, so we'll have, so I omega 1 plus 0 equals I omega 2 plus m v squared v2, L over 2. So we can substitute now the equation for v2 that we have earlier. So this becomes, so I omega 1 equals I omega 2 plus m times 1/2 E L omega 1 plus 1/2 L omega 2 times L over 2. Then we can replace I here with the equation for the moment of inertia. So since this is a bar or a rod, so the moment of inertia is given by 1 over 12 m times the length squared. So our equation becomes so 1 over 12 ml squared omega 1 equals 1 over 12 ml squared omega 2 plus 1 over 4 ml squared e omega 1 plus 1 over 4 ml squared omega 2. So simplifying the equation, so combining the like terms, so we'll have 1 over 12 ml squared omega 2 plus 1/4 ml squared omega 2 equals, so 1 over 12 ml squared omega 1 minus 1 over 4 ml squared e omega 1. So further simplifying the equation, so this becomes, so ml squared omega 2 minus ml squared this should be plus 3 ml squared omega 2 equals ml squared omega 1 minus 3 ml squared e omega 1. Then, further simplifying, so this becomes 4 ml squared omega 2 equals, so ml squared omega 1 times 1 minus 3e. And then, finally, so omega 2 is equal to 1 over 4 times 1 minus 3e omega 1. There. So, this is our equation for the new angular velocity, so omega 2. Now, substituting the values to solve for omega 2, so we'll have, so omega 2 equals 1/4 times 1 minus 3 times the coefficient of restitution 0.6, then times the value of omega 1, which is 6 radians per second. So, we'll get negative 1,200 radians per second. So, the negative sign here indicates the direction. Therefore, we say that omega sub 2 is equal to 1.20 radians per second clockwise. Now, solving for V2, so V2 equals, so the equation for V2 from earlier is 1/2 L E omega 1 plus 1/2 L omega 2. So, substituting the value, so we have 1/2 times 0.200 meters times 0.6, then 6 radians per second, okay, plus 1/2 times 0.200 meter times 1.20 radians per second. So, this is equal to, so V2 is equal to 0.480 meter per second upward or up.